Today's talk will be on fuzzy logic.
And you think you have problem to sleep? Well, the point is that we will clear everything during the lecture. I was, as you heard, asked a week ago if I could speak about automotive cooperative vehicles, and when Arnaud asked so nicely, I could not say no, and I started to do some research. And we will see the result of that today. So
It's the other one. It's the other one.
Yeah.
So sometimes things which seem complicated can be very easy. And we will try to make things easy today by stepping back to basic and say what are we trying to solve, what are our physical limits, and connect to what we said earlier this week. So my research, well, as a skilled researcher, As a skilled researcher, I cannot handle Outlook in PowerPoint. But I started to search on the internet and said, okay, cooperative driving, what is this? Look at this crossing.
Whoa.
Who is cooperating? It's a very safe ending here, you say, or happy ending. But there are several things we could observe here and say that, okay, they are more lucky, they avoid a crash, but we have some pedestrians walking out here. We have someone who is in a hurry. And actually, maybe the most interesting, in the middle of the crossing, maybe some of you managed to see, but there is one vehicle here, I think it's coming now. And you see a small, some smoke up here. That's actually, I think, the only one in this traffic situation who reacts and probably avoids an accident. So we look one time more. It brakes very little and very late, but probably saves a half a meter or a meter. The pedestrians, you can see they react, they stop and start to observe, and then they continue walking. Okay, this was not a test drive of us, but we will test drive a scenario like this towards the end of the talk. So now, okay, let's do some basic simulations. So we will look at the situation where we have vehicles going in the same direction, and you have one vehicle trying to get in and pushing the other vehicle to give space, basically. And we will just observe the dynamics. So we will start with some basic models. So I will jump to MATLAB now. All screens became black. Okay, let's open the first file. So this is a very simple model of someone or who's monitoring a positioning system. So with a small integrator here, we model the position of the vehicle, and this driver wants to do a lane change basically, but drives with closed eyes. So then we expect something like this, just to explain the model. we do a steering input. We don't look where we're going, so of course we disappear. And then we extend the model. This is a slightly more advanced driver. We want to do the same lane change, but observe where we are going, and we make a correction. So we take the difference between the position where we want to be and the position we have here. And then we have a small controller here adjusting depending on how big the error is. So we would like to have a step, but of course no one can do that. So when we decide to change lanes, we have a smooth change. So this is our first driver, and now we will include a second driver, and we will include some interaction between them. So we take the third model here. So we have the first driver up here, and the second driver who is already on the street, which observes the distance to the first one here. And this driver wants to be one lane away from the other one. So we take that position and add them together. And then we have the same dynamic here, basically. And let's look at the two outputs. Okay, the yellow one we recognize is the first vehicle, just changing lanes like before. The other one observes that, oh, someone tried to get into my lane. And we see the response is slightly slower here, because first, when this starts to show its intention, we start to move here. We could make this more advanced. If this driver is looking and predicting that this one will come, maybe we give some space before. We could also say that, would this work in our situation if this driver is not very observant and is slow in the response? Well, maybe it would be dangerous if we react first over here. And that's a key point here, that delays and slow response gives us problem. But we're especially interested actually in something which we are still missing in this model. Because here we basically model how the first driver influences the second one. But in most traffic situations, this driver trying to get in also observes, do I get some space? So we miss how this driver actually compensates for the second driver. So let us go on to the last model. So here I included a connection back. I also included two delays, because when we start to have connected control systems and feedbacks, it's the response time of each vehicle and delay times which limits the performance of our system. So let's look at the first simulation here. And we see that now it starts to get interesting. The first vehicle starts like before, but somewhere notice that, hey, the guy next to me is not giving me space, so I'm prepared to go back. But I realize that, well, anyway, there is space, so I change my mind again. Things like this we typically want to avoid. Here we should say that this happens because they are both react about with the same speed. So we will make, we keep the delay. Both delays are 1 second here, but let's make the driver who is already on the lane will be much more reactive. So we speed up that controller. And let's redo the experiment. Wow, we are back. So this is a first observation which we will try to use soon when we conclude which traffic situations are dangerous or potentially dangerous and which are more likely to be safe. We saw that we had two players here, two vehicles. It could be one vehicle and one pedestrian, or a biker and a vehicle also. But we have two agents interacting, and we made this one much faster. And the other one is then the slow one here, and we still see some effects of the interaction, but much less, no oscillations. So this one is, it's funny, they look, we don't see that the blue one is much faster, but we only see that if we go and analyze here. But this one starts to make a change due to the step input here. This one reacts, you see we don't have the slow start now, so here we see an effect that it's actually much faster. So it reacts almost immediately when this starts to make a change. But it's not immediate. But this one is slow, so this still takes some time here. The slow one doesn't have time to react to the slow response. So basically it reacts to the response up here when it's already up, say, here somewhere. Let's do the other way around. We make the lower one slow, like before. And the upper one fast. So we can conclude two things. It's good to have a fast, one of them acting fast and one slow, but it has to be in a special order. If the order is incorrect, we have a dangerous situation. Whoops. So let's go back to the presentation. Okay. So some conclusions here. Normal traffic, when you have vehicles of some kind interacting, it's a distributed control system. You have controller basically in each person. And each one moving around, you can analyze. And I mean, there's a lot of control system inside the vehicle. But then when they interact, we get additional feedback. And the effect of this additional feedback, that's our problem. So that's somehow we want to understand that. Well, to some extent we already understand it. Make one fast and one slow and make it in the right order. But if we have these connections, it could be hard to find out where they are, what are people looking at, what influence their decisions. And humans are not so easy to analyze as the small models I had here. So this interaction is actually the trouble. And now Arnaud wants me to speak about them. Delay. I mean, if you're a control engineer, you go around and check that you don't have any delays in your system, or you try to minimize them, because delay, that's the worst thing you can have. If we have humans in our system, it's very hard to avoid a delay. And approximately in the order of 1 second, we have to say there is always a second, normally more. So we can, as long as we have humans there, we have that delay. So that's something which limits the performance. And this is still, when we assume that the human is cooperative, trying to behave as they should. If we go to, for example, children, and we say that something unexpected could be happen, it's much worse than this. Okay, in control theory, we say what we have with these two vehicles, it could be rearranged to something which is called cascade control. So those of you who had control should recognize this. Cascade control is when you have two feedback loops. So here we have a measurement and making correction. Here we have measurements and make correction. And this is often a very good strategy. And if the inner loop is made much faster, we have fast dynamics here, and the one is slower, it works fine. Often in automated driving, we could have this, for example, we could have velocity control here, which is done internally in the vehicle, and then maybe we have a positioning. If you want to control the position, that could be the outer loop, where we do slower corrections. If the time constant between the inner and outer loop of the dynamics is large, you could say that we could analyze this one independent of the outer loops. So the analysis is much easier. But if the time constant is about the same, then we have to consider both feedbacks in the same time to find out if this is stable or not. So that's, again, referring to some well-known control strategies, a reason why we want to do one of the controller fast and make the other one slow. And if we use this insight now and say, how should we design our traffic solutions? You say the main rule should be that we should have different speed, and the one who decide slowly or change decision slowly should have priority, and the fast one adapts to that one. So let's analyze a few traffic situations and see who is the fast one and who is the slow one. Okay, pedestrian crossing. Who decide fast? We have a vehicle approaching rapidly. Well, maybe not on this road, but let's say it comes in 70 kilometers per hour, and we have a pedestrian. So Arnaud, now it's my turn. I mean, you gave me a week, I gave you 10 seconds.
So we're reacting fast. Huh?
Yeah, the car is approaching fast. The driver is awake. It's a French male driver. So he's very observative to the young woman.
Sure. But you would like to be very close to this young woman, so I would react very quickly. My parents always told me I should react as a pedestrian very quickly, all the traffic.
Yeah. And the thing here, which I think, I mean, if you think a little bit, it's not hard, but the first thing is the car is fast, but actually the driver needs a lot of time to change. With high speed, I mean, you cannot brake very rapidly. I mean, at least take some 10-20 meters. So the fast vehicle is the slow agent in this situation. And the pedestrian can very rapidly decide to step out into the street or not. And that's, I think, what makes this traffic situation very dangerous. Because safely, or if it's going to be an accident, except if it's Arnaud driving, will be on the pedestrian. I mean, most of us are a little bit nervous stepping out on a pedestrian crossing when a fast vehicle is approaching, because we know that if they don't observe us, it's soon too late.
But, I mean, the woman is behind a big white van, and equally the car has the white van blocking view. The car should not be driving fast.
Yeah, Now I did this research on quite rapidly. I picked the next picture I could find on internet. So what we are thinking about now, I mean, we could add and make the problem more complicated. But the first thing is that actually neglect all other vehicles. And the point is that a fast driving car actually is slow in changing decisions. So that's the main point here. Of course, if the driver acts early, but what they do is that they predict, because if they are close, they cannot change the decision basically. But the pedestrian can be very close to the car and change decision. But you could say, from a natural or physical point of view, it would be natural if the pedestrian is the one who decides who go first. And you could think in most countries today, pedestrians have the right of free way, but still it requires that the pedestrian show the attention so that the driver has time to react. Okay, a railway crossing. Here we have a driver who misunderstood, also misunderstood the sign here, but I mean, it's a very clear thing. A train needs several kilometers to stop. So although it's coming very rapidly, it's the one who is very slow in changing what it's doing. The car should approach slowly and check. So the slowly moving car is the one who is fast on changing their decision in this situation. And here the hand wheel did not work. Another typical situation, two vehicles. We have one who stopped here. It's that vehicle which actually can quickly decide to go in or wait. And the vehicle coming with a high speed has no chance to avoid an accident if the other one takes the wrong decision. And typically here you have the traffic rule set to follow this principle. So the blue one should not enter if it's not a freeway. But as soon as we give some time to the green car here, you could go in, this one observe and slows down and helps avoiding an accident. Then we have funny traffic solutions. Here, since I was a child, in Sweden we had middle lanes which could be used for traffic from both directions. You had vehicles here, and if you had to pass someone, you use the middle lane. And I'm not surprised it disappeared, because when you're driving your lane, there is impossible to interact with people coming against you, basically, because things are happening so fast. You have too slow agents, and if you share this resource and you cannot interact, it becomes very dangerous. Okay, so let's look at the situation where we have humans and we have an automated vehicle. So this is research together with CIV2018. We have an automated vehicle. The path of the vehicle will be animated, but it's a real driving vehicle. We have a crossing pedestrian, but we don't know anything about the pedestrian, so we have the pedestrian as uncertainty here. The pedestrian can take different ways. Here, there is a pedestrian, you just don't see it. So the vehicle has to slow down, and the pedestrian passed, the vehicle continues. And we don't model any interaction here. Instead, we say that, okay, the pedestrian can take any way with equal possibility, but we think it stays on the pavement or the crossing. And here we should see again one time the vehicle passed, there is no pedestrian, and we compare that to the solution that the pedestrian crossing here. So, this is the way I think the problem is solved today. We add uncertainty around the pedestrian. We try to limit the uncertainty. So in this example, we assume that the pedestrian stays on the pavement, but we haven't modeled the interaction. The vehicle slows down, so actually both are can decide quickly. Both the pedestrian can change the decision, the driver can change the speed very rapidly because the speed is low. The driver can stop within a couple of decimeters. Okay. So let's conclude as what we got so far. We have a human in the loop and we want to cooperate. Then the pedestrian is the fast one, which is a pedestrian, or in the three examples we looked with the train, it was a vehicle which was the fast one. In the third T crossing was a still standing vehicle. Those who are fast, they cannot be allowed to surprise the other agent, which is considered slow, but might move quickly, but they are slow in changing decisions. So this must be a principle. And here we see that, of course, there is very hard to place children in this, because they can always surprise us. Or humans who is behaving badly. So that's very hard to have an efficient solution if we have these possibilities. The natural algorithm is to let the fast one to change decisions, to observe the one who is slow, and the fast one decide depending on what the slow one is doing. And then we have the natural, that's the slow one, has priority, like for the train or the T-junction. But then we also have traffic solutions today where are, you could say, unnatural. If the pedestrian has the right to freeway, but the vehicle cannot always stop. And something also to note, I mean, as soon as the vehicle slows down, it changes from being slow in decision to be able to be fast. And there you could also have, when you slow down for a pedestrian at the crossing, for example, suddenly you are shifting your situation to a system where you have two agents who can decide about equally fast. You can have these stability problems, which we saw in the beginning, between a pedestrian and a car, which would mean that the pedestrian is basically hesitating, and the driver is also hesitating who should go fast first. So this gives us a dilemma. The autonomous vehicle does not suffer from this 1 second reaction time, but when the speed is high, it is slow in the decision. It falls back to Newton's law and friction and so on. And then it changes with the speed if the autonomous vehicle is a fast decisioner or a slow one. But as soon as it's a slow one, it's very hard to take responsibility for the safety. And all this have been covered by the earlier lectures in one way or another. And in traffic situations where we have the human as the fast player, safety depends on the human. So you can say that we have to trust the human. If we don't, we have to slow down the system very much. And that's the dilemma. So what can we do? Well, the easy solution, take away the humans. They have delays. We don't like delays, so we take away the problem. We do that today. That could be good to just reflect on. I mean, if we put up a fence, we could drive fast even if there are children there, as long as they're not close to the crossing. So we know exactly where we have to slow down. We can replace junction with more infrastructure. These solutions can be expensive or time-consuming, so there are drawbacks. So if we want to do it another way, let's look at cooperative solution for self-driving cars where we don't have any humans, and see what can we do. We often have like a master and slave philosophy. The master receives information from the slave. We could have many slaves here, and the master takes the decision, and it's up to the slaves to follow it. They must obey it. Not very democratic, but you say what this is basically that the slave corresponds to the one who could decide fast, and the master is the one deciding slowly. So if we design our control system correctly, with fast and slow decision making, we can get to this. And the nice thing, I mean, this is the slow connection basically. So there is very little feedback in that direction. So there should be less control problem here. And let's see how we use this to construct an algorithm where the master do some calculation and allocate time slots for each vehicle to pass the crossing. So the principle is very simple. We formalize this as Christoph described yesterday as motion modeling. The path for each vehicle is assumed known, so we just have to decide upon the speed. We have dynamics of each vehicle. We have information where the intersection starts and stops. So that's our critical area where we only want one vehicle at a time. We could define the time when we go in and go out of the crossing. And the important thing is that the time interval we are inside in the crossing, we use that for safety constraint. So we see here that two vehicles, the time of one vehicle and the time of the other vehicle, they should never be intersect. So there should be only one at a time. And we plug this into, we need, of course, communication, receiving and sending information, and this is often the weak point, because it could be vulnerable. And with all information, we could set up a receding horizon control program, also exactly like described before. So we have some criteria we want to fulfill. Typically, we want the vehicle to deviate from their preferred speed as little as possible. We can take comfort aspects here, how much jerk we have. And then we have a lot of requirements which have to be fulfilled. So this is a mathematical modeling problem to formulate the problem this way. And in our research, a lot of the research is basically to formulate the problem like this in a way so it can be solved in real time. But when that's done, we could illustrate what's happening. Here we have time on this axis. We have one vehicle approaching the intersection, which is up here. So we don't consider from which direction this vehicle is coming. We are just interested at which time we enter and what time do we exit the crossing. So if we add a second vehicle, so both vehicles are far away. They come from different directions, but we don't see that here. With a set speed, we conclude that there is a conflict here. So early on when they approach, they get information, they send information, and they get back information from the master, how they should adapt their speed. And the nice thing is that they don't need to adapt very much. If they get the information early, they don't have to accelerate very much or brake very much. So this could be good from an environmental perspective too. So small speed adaptation, and the second one enters after the first one. And this is done in a receding horizon. So if we have a third vehicle approaching faster, we see. So suddenly it's within the near area of the crossing, communication again, and a conflict is detected. So the control scheme is repeated. And the nice thing is that the two first ones, they don't have to adapt so much now. So when all vehicles are approaching, typically you do smaller and smaller adaptations. Of course, if we would have a human here who could give us a surprise, this would be a big problem. So here we assume that we have all agents are following what they're told to do by the master. Okay, let's look at some experiments. Here you see communication. Here you see speed change. So the second communication is almost no speed change. We have three vehicles approaching. And of course we use students as test drivers at least. Here we see a parked vehicle. That's used for the communication. So here we have a communication we could trust fairly well. So it was a Wi-Fi station there. And from above, we even gave the students a little bit of safety margin. And here we had the coordinator. What we could conclude from this is we needed to communicate very little. If you once communicated and there is no surprises, it's quite easy to keep the speed. We repeated almost the same thing. So this is together with one manual-driven vehicle. So that's a big difference. We also use a 5G network here, so we don't have any dedicated communication platform near the crossing. Yeah, so this is a company behind this. So Ericsson have equipped this proving ground with the 5Gs, and this test driving was the inauguration of that network. But it was just shown quickly here. One of the three vehicles was manually driven. So how do we get in this manual driven vehicle together with the two autonomous ones? Well, we predict. We don't have a bad behaving driver, so the manual driver tries to keep the correct speed. And since the speed is not very low, the manual driver cannot change the speed very rapidly, but cannot also not keep it very extremely accurately. But the updates is then sent to the other vehicles, and then they add a kind of a safety distance to the manual vehicle. If you have one manual vehicle together with the other one, which are self-driving, I mean, you could do some very rough calculations, and this is the ideal case. So if the vehicles would approach with 70 kilometers an hour, if you could brake with 1G, which is quite rough braking, then you say, well, if you're closer than 20 meters to the crossing, you cannot avoid entering the crossing. But up to 20 meters, if you do full braking immediately, you can basically stop before. So at 20 meters before is the last chance to decide to stop. So if we have a manual vehicle and we think it can behave strangely, this is the point of no return. And if we say that we have 5 meter long vehicles, 3 meter wide, and we put a box around them, then with this calculation, you can say that between each vehicle we need 8 meter empty space, which means that if we add the 5 meter of the vehicle, we can have one vehicle every 30 meter in each direction. And if we compare that actually there are 2 roads sharing this, we can say that, okay, the efficiency of this crossing would be to have two vehicles every 13 meters. So we are wasting 3 meters. And per vehicle, we waste 1.5 meters. That sounds very little, but you could say if you compare with the length of the vehicle, we lose 30% of the space. But that is basically all empty space between the vehicles. Also, if we would have only one direction here and drive in a platoon, we would have some safety limit. But this is the ideal case, so typically you have to add more space to this in real cases, of course. But what this shows is that it seems not to be extremely bad to have a manual driven vehicle in the middle of the automated ones. But we are in that case where all the vehicles make slow decisions. It takes time to change the speed. If we would have a pedestrian who could step out here, of course it would be a different. And we could also say that although this shows that it can be quite efficient, if we would form platoons and let several vehicles from this direction pass before we switch, we would get even, we could lower this distance to make it more efficient. I said that the communication is the important thing. If we have humans there, we have this 1 second delay. Here we have technical communication, and if that fails, so we have package drops, we might have unknown delays. So this is a very important bottleneck. Can we trust the communication? There's a lot of research going on, and this is an advertiser for Mohammed, who's a PhD student at my department, who is investigating especially how the performance of the communication system influence the control possibilities. And there are work done on to design the control optimally. The other work done on design the communication optimally. But in the end, we want to optimize them together so that we don't have suboptima. And that's what Mohammed is doing. So this cannot be understood from this slide. So this is advertising why you should go and speak with Mohammed. But Mohammed is investigating with different communication scheme, how much does it influence the performance of the whole system. So you see, without knowing exactly what that is, we have cost on this, and this is how different scheme perform. So let's sum up. How do we include the human? Can the human be one of the slaves following the master? In this crossing driving, we saw that it seems to be at least not impossible, but there is a lot of things to investigate around this. How much uncertainty do we need to add around a human in the loop? How much are they unpredictable? One thing is uncertainty in position, but it's also uncertainty in reaction time. Also, can we trust that the human is trying to cooperate? So how should we handle misbehaving humans who try to take advantage? If they know that the other vehicles are safe, they could basically take a free way and let the other one wait. So I think these are, I know maybe have a lot of other suggestions and inputs, but I think these are kind of fundamental things we have to consider. And with that, I conclude my talk. Thank you.